Welcome back. In this set of videos, we're going to deal with the topic of dimensional analysis. So at the end of this series of videos, you should be able to understand and use the Buckingham Pi Theorem, which will be introduced later in this video. We'll devise fluid mechanics experiments identifying the key dimensionless groups and apply dimensional similarity to extend results from one environment to another. Okay, so what is motivating this particular chapter? We know that most fluids problems need to be solved experimentally. Okay, so fluid mechanics is governed by what are called the Navier-Stokes Equations. They are brutally difficult to solve, and even computational fluid dynamics cannot answer all of our questions. So oftentimes we need to solve these problems experimentally. An experiment might be conducted in a lab, right? So think of a wind tunnel or a water channel or something like that. How do we extend these results to the real world where parameters such as the size, viscosity, density in the lab might be different to these similar parameters in the real world? In addition, fluids problems have numerous parameters, right? So density, viscosity, free stream velocity, things like that. How do we reduce the parameter space of the problem? Let's say we're trying to, characterize the drag on a car, right? It has a pretty big parameter space, right? We can deduce that the drag might be dependent on the velocity of the air, on the density of the fluid, on the viscosity of the fluid, on the size and shape of the car. So there's quite a few parameters to consider, right? And so if we wanted to have as big a picture as possible, we would want to vary all of these parameters independently. And we can see that this would quickly blow up, right? Because we have too many parameters to vary across a range of values. So the question here is, how do we reduce the parameter space of the problem while still being able to capture all of the different effects? So this is the domain of dimensional analysis. Okay, so as a quick case study, let's consider the flow past a cylinder. So a typical question an engineer might want to answer is, what is the force applied to the cylinder by the fluid? Okay, so what is the force applied to the cylinder by the fluid? We could call this even the drag force, D. Okay, drag force. Now from intuition, most engineers might say that this force depends on numerous parameters, right? So we have a free stream velocity, so it might depend on the velocity, which we'll call U, maybe the density, that's rho. We can anticipate that the diameter of the pipe would also affect the drag force, and the viscosity. Okay, so let's say we consider 10 values of these 4 parameters. Okay, so 10 values here, 10 values here, and so on and so forth. And we varied them independently. How many experiments would we need to run in order to capture all of these permutations? The answer is that we would need to run 10 to the 4 experiments. And let's be honest, no one has time for that. So can we somehow reduce the number of parameters? In this case, we can compress the problem quite a bit by defining what we call dimensionless parameters. Okay? And we'll get to formalizing these a bit later on. But for example, the drag force can be non-dimensionalized in terms of what we call a drag coefficient, where the drag coefficient is equal to the drag force. And you know what? I will call drag force, we'll denote it as FD to make it different from the diameter, which is uppercase D. So we have FD divided by 1/2 rho U squared multiplied by A, the area of the cylinder. So this is what we call the drag coefficient. And again, this is dimensionless. And I encourage you to, plug in the dimensions or units in SI, let's say, and you'll see that all the units cancel out. And this is a dimensionless parameter called a drag coefficient. We can also define another important dimensionless parameter, which is called the Reynolds number, which you have seen before. And this too is dimensionless. In fluid mechanics, there are several very important dimensionless parameters that you will see in this course and in your subsequent study of fluid mechanics. And so definitely the Reynolds number is one of the big ones. Drag coefficients or just force coefficients in general are also very important. So what we see here is that the problem can be reduced to a CD versus Reynolds number curve. Okay, notice that we have all of the required parameters, velocity, density, diameter, and viscosity, appearing in CD and RE, the Reynolds number. So all of the relevant parameters are included in these two dimensionless parameters. So we can create, or the experimentalist will just report a curve of drag coefficient CD versus Reynolds number. And for this fictitious flow, it might look something like this. And this CD versus Reynolds number curve is valid for many combinations of velocity, density, viscosity, diameter, etc. And so this brings us to the concept of similitude. Okay. So if we have two individuals, an experimentalist who is running this experiment in a lab and an engineer working in the field. So the experimentalist will run in, let's say, a wind tunnel, this experiment. And in that particular wind tunnel, the parameters will be relatively fixed, right? So most likely, the experimentalist will not be able to vary the viscosity and the density. However, the experimentalist will be able to vary, let's say, the wind tunnel velocity and thus affect the free stream velocity u, and potentially the diameter as well. The experimentalist could consider several cylinder diameters. So thus, what the experimentalist will be able to do is independently vary the Reynolds number through changing of the velocity and the diameter, and the drag coefficient as well. Okay? And so in the published report that the experimentalist will write, the force will be presented as a drag coefficient plotted against the Reynolds number. And so if we have an engineer in the field, the engineer doesn't have time to run an experiment. So most likely the engineer will look for any published results. And let's say the engineer wants to estimate the drag on a cylinder moving through water, let's say. Okay, so he or she is not going to run the experiment independently. It's going to look through some published results, and the engineer is only interested in a particular case, right? The case that is applicable to him or her, right? So in the field, it will have a certain density, viscosity that might be different from that in the published report. But that's okay. Okay, so the concept of similitude would tell us that we just need to calculate the Reynolds number for the problem in the field, and then just match it to the Reynolds number in the published report. And then the engineer would get a drag coefficient, and then can work out a dimensional drag force based on the parameters in the field over here. Okay, so this is valid because both the experiment and the engineer's problem were similar. And so what do we mean by similar? So the geometry, for the most part, is fundamentally the same. Okay, despite the fact that maybe the diameter in the published report and the diameter in the field for the engineer might not be the same, they scale in the same way, right? So the proportions are more or less the same. And another thing that would be very important as well for similitude to apply is, for example, that we are comparing the same fundamental flow. So let's say we have the free stream velocity u is approaching the cylinder at the same angle in both the experiment and the engineer's case in the field. Okay, so in this example, the relative dimensionless groups, being the drag coefficient and the Reynolds number, they were given to us in this particular case. Okay, but this leads us to a question: is there a systematic way to determine how many dimensionless groups are needed given a certain list of variables that we know are fundamentally important for a given problem? And this will lead us to our next topic, which is the Buckingham Pi Theorem. So in order to determine how many dimensionless groups are relevant to a certain problem, we make use of a very powerful theorem called the Buckingham Pi Theorem. The theorem states the following: an equation or problem of k variables can be reduced to a relationship of k minus r variables, where r is the number of reference dimensions required to describe all the variables. Okay, so what this is saying is that if we have k variables that are important for a given problem, such as velocity, density, diameter, viscosity, for the case of the flow past the cylinder, we can reduce it to a problem of k minus r variables. So k minus r will be the number of dimensionless groups that we end up with, using this Buckingham Pi theorem, where r is the number of reference dimensions. Now, what are these reference dimensions? So recall that in fluids, well, in pretty much any study of physics, we have typical primary or reference dimensions. In an introductory course such as this one, the typical ones that we're going to deal with are mass, length, and time, where mass we denote it as m, length has the variable L, and time t. So notice that this is not dependent on the system of units that you're using. These are just dimensions, right? So in SI units, your length will be in meters, and your time will be in seconds, and your mass will be in kilograms. Okay, but this Buckingham Pi theorem is agnostic to the system of units that you're using. Okay, so let's see how this is applied to our case study of the flow past a cylinder. So we had stated that the drag force, Fd, is a function of the viscosity mu, the density rho, the velocity u, and the diameter d. So in this case here, the drag force relationship here, we have k is equal to 5 variables. Okay, so we have 1, 2, 3, 4, and 5. So now what we need to do is look at the dimensions of these 5 variables and see how many of these dimensions appear. Okay, so we're trying to find this R, where R is the number of reference dimensions or primary dimensions that appear in these 5 variables. So density has dimensions of mass over L to the power 3. The velocity u has dimensions of length over time. The diameter d has dimensions of length the viscosity mu has dimensions of mass over length and time, and the drag force has dimensions of mass, length over time squared. So what do we see here? We have mass that appears, we have length that appears, and we have time that appears. Okay? So all 3 primary dimensions appear. So we find that we have R is equal to 3. So what this tells us is that we can reduce our original parameter space with 5 variables to a new space of k minus r. So 5 minus 3 is 2. So the number of dimensionless groups that we will need is k minus r is equal to 2. And this is in agreement with what we found in our case study over here. So all we need is 2 dimensionless groups to fully represent this problem. And these dimensionless groups are often called pi groups. So what we do in general, so let's just write this, in general, we seek to reduce a relationship of, let's say, some sort of variable u1, which could be a function of u2, u3, all the way to uk, to a relationship between dimensionless products. So in general, so we want to reduce this to dimensionless relationship, which we would call pi1 is equal to some function of pi2, pi3, all the way to pi, but now this won't be k, but k minus r. So where k minus r is less than k, of course. So this is what the Buckingham Pi Theorem allows us to do. It allows us to reduce the parameter space of our problem by helping us to determine how many dimensionless groups we need. But what is important to realize here is that the only thing the Buckingham Pi Theorem tells us is how many dimensionless groups we can reduce a problem to. It doesn't tell us, however, what these dimensionless groups are. And what we will do in the next video is find a systematic way to determine what these dimensionless groups look like.